Welcome back. Today we're going to talk about lesson 9.2, doing a significance test for P. So what are we doing? We are trying to figure out, we've been doing confidence intervals. We've been talking about does data fall into a certain range. Then last time we talked about how we have this hypothesis, right? So we make this claim and we say, 35% of Netflix users watch this, okay? And then the other one is the alternative hypothesis. It says, no, I think it's less than that. And so whenever we make this claim, we're going to have to do a test. And so the test is going to look actually fairly familiar. We're going to be using variations of formulas we've used before. We're going to test for conditions that we've tested for before, and we're going to spend some time looking at what's the probability of something happening, and then evaluate that probability and say, that would make our hypothesis, that would support our hypothesis, or we don't have enough information to support the null hypothesis. So let's look at what happens here. Well, first of all, we get into a situation. Let's look at this problem down at the bottom here. According to the U.S. Census Bureau, the proportion of students in a high school who have a part-time job is 0.25. An administrator at a local high school suspects that the proportion of students at her school who have a part-time job is less than the national figure. She would like to carry out a test at the alpha equals 0.05 significance level. Okay, so think about what that means. The administrator selects a random sample of 200 students from the school and finds that 39 of them have a part-time job. Okay, this is how life works, right? So we're just going to put a process on it. Somebody says, "Oh, dude, there's a 50% chance of that happening," and you're like, "There's no way it's that high." And so they say, "Yeah, it is," and you're like, "I'm going to do a test," and you go ask a bunch of your friends. Well, all we're doing is we're putting a little bit of formality on it and saying, okay, we've got this hypothesis null. 25% of people have a part-time job. The alternative hypothesis is this administrator thinks, oh no, it's less. So now we have two hypotheses, and we're going to test it to see what exactly is going on. Is there enough information to support this national figure that says 25% have part-time jobs, or do we have to support the null and say, no, it's less than that? So here we go. What are our conditions to make this happen? Well, obviously we have to have a random sample. We have to have a random sample because it's got to be representative of the population, right? We can't introduce that bias. 10% sample. Again, making sure that we have a sample that's representative of the population. So our 10% sample has to be less than 1/10 of the population. And also we have to meet the large counts condition. Which is n times p greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. Okay, so that should be a 10, 1, 0. All right, so those are our preconditions. So you do a problem like this, you've got to test those conditions. We should see check, check, check. Yes, those three things happen. Here's what the test looks like. What we're going to be doing is we're going to be using a standardized test statistic. And what we're going to do is we're going to say, is our statistic that we have compared to what the claim was, is it, how far away is it? What's the probability of getting our test statistic that's that far away from the mean or the true statistic, the null statistic, okay? So here we go, test statistic. And our p-value. So like I said, think about it like this. We have this curve, and it's normal. And what we're actually evaluating is the mean p-hat, because it's the test statistic, right? It's just this claim, and we're evaluating this claim, and we're evaluating what we actually have when we did this little test, right? So this administrator is going to do this sample. And our standard deviation of p-hat. And here's what we've got. And these formulas should look way familiar to you, right? Because in this case, we're talking about a proportion. So our p-hat here is our p, that's our proportion that we're talking about, and then our standard deviation is p times 1 minus p over n, and it's the square root of that. So what's our z value in this case? What are we evaluating? If you think down to that example that I just talked about, really we're not comparing like our sample mean to a mean z-score. What we're doing is we're saying, okay, I have this claim here, this h sub 0 claim that says it's 25%. What I found was this, and there's a difference between those two things. What's the probability that that difference actually happens based on, and it's going to be the standard deviation, right? So if I think of the normal curve, here's the mean. As I get more standard deviations away from the mean, it becomes less and less likely, right? And that's where we get into these tails, right? So this over here, it's like very unlikely that it's happening by chance. We're doing the same thing here. And what we're going to test is we're going to say z is equal to what we got minus the claim proportion over our standard deviations, p times 1 minus p. And then I'm going to put that over n. And this is going to give us our p-value. And the p-value is a probability that whatever statistic we got happened by chance. So let's look at an example here. According to the U.S. Census Bureau, the proportion of high school students. So we've got this administrator that says that 25% seems a little high. I'm going to test. So what he got was 39 out of 200. And so we want to state the appropriate hypotheses for performing the significance test. Be sure to define what the parameter of interest. So h sub 0 is equal to the original claim. 25% chance that this is that a student has a part-time job. What's our alternative hypothesis? Well, this is where you look at the context of the problem. What does the context say? The context says the administrator thinks that p is actually less than 0.25. And in this case, p is the proportion of students local high school students that have a part-time job. Very important to define that. Now, explain why the sample result gives some evidence for the alternative hypothesis. Well, look at what happened. This is life, guys. So, right? So somebody says 50% of the time this happens, and you're like, no, it's way less. You go ask your friends, and you find less than 50%. Well, the explain would be this: 39 of 200 is equal to 0.195. So this administrator asked 200 people, and only 19% of them, much less than 25%. This is less than 25%. So we want to check the conditions for performing the significance test. So now we've got this support for our alternative claim in theory, right? So we think to ourselves, well, it's true. What if he had found 25%? He might not go beating down the doors of everybody to see, but he gets this 0.25%. Well, he might not investigate. But what he got was less. And so he's going to investigate the claim. So are the conditions met? Well, 200 times 0.195. Oops, we're testing the claim. 0.25 is equal to 10. Greater than or equal to 10. All right, it's actually equal to 50. And then 200 times 0.75, 1 minus 0.25 is greater than 10 because that's equal to 200. This is 50, right? So that condition is met. So next what we're going to look at is it a random sample? Well, when we look back in the problem here, what we have is an administrator at a local high school suspects that the proportion at her school who gave a part-time job is less than the national figure. She would likely carry out a test. Alpha 0.05 significance level selects a random sample. So right there, because this is a random sample, we're going to take that from the problem. So random, we can say yes, and we can quote it. We can say random sample. Excuse me. So then we want to see if the 10% condition is met. So we're going to evaluate our sample size. So what we have is that there are 200, and we're going to say that that's less than 1/10 of all students at the school. Okay, and how do we know that? Unless they're pretty specific, the 10% condition is probably going to be met in this case, but we're also saying that from the school, they're setting us up to be able to do this. They're not setting it up the other way. Okay, so they didn't give us a number in the high school, and typically that's what will happen. They'll give you a number in the high school, and it won't be less than 10%. But in this case, we don't have an idea of what it is, so we're going to say that 200 is less than 10% of all students in the school. So what are we doing now? All right, so now we're going to actually calculate that standardized test statistic. So what do we need? Well, we're ultimately looking for a z-score here. And that z-score is going to be based on taking our sample here, our sample statistic, and we are going to subtract from that, we're going to find the difference between that and what the claim was. So in this case, that's going to be equal to our 0.195, which is what the administrator found. And we're going to subtract the 0.25 that was in the claim. And on the bottom, we're going to put the standard deviation. Well, the standard deviation is based on the sample proportion. And so our sample proportion was our p, and then we've got 1 minus p here, and then we've got n. And so that's going to be square root of 0.25 times 0.75 over our number of people, which was our 200. And so when we actually calculate this, we get that that's 0.195 minus 0.25 over 0.306, which gives us a z-score of negative 1.797. And that actually makes sense, because if our z-score is negative, and that means it's below our sample below that value that we were looking at, in this case, the proportion that we were subtracting, right? So our 19.5 is below the 25. And that's about equal to negative 1.80. And if we check out our table, what we get is that the probability of that happening is 0.036. And so what we are looking at now is we're saying here was our claim here. This is our 0.25. And our standard deviation here of p hat was equal to 0.0306. And so let me sketch a little picture here. What that would mean is, if we've got this normal curve here, and the probability here of 0.195, this right here, is below the 0.25. And sometimes drawing this picture can help support your evidence there, right? And so what are we comparing it to? Well, what is our alpha level? Our alpha level is 0.05, so that's our significance level. So what conclusion would we make? Well, think about it like this. We ran the simulation as if here's our 0.195. We're going to compare that to the 0.25, and then we did the standard deviation as if there was a 0.25 there, right? So what we have is we are evaluating our 3.6% chance of that happening against a 5% threshold. So what we just said was there's only a 3% chance that this happened by chance. Well, so that would mean that we have convincing evidence like of all the samples that could happen, we just happened to pick the one that was 3.6% likely? Not likely. So we have convincing evidence against the null. Because remember, our null was that the actual proportion of students was 0.25. And so we have convincing evidence against the null. And what we'd say is that 0.036 is less than 0.05. And that points out that our proportion that we calculated, or our probability that we calculated, is less than the alpha value. And so we would say the proportion at this school is less than 25%. So think about how that just went right there, right? We defined our null hypothesis. We said, hey, it's 0.25. But the administrator thought it was less than. There's our null and there's our alternative. So then, what evidence do we have? So it's like any other claim, right? So if someone says something and you say, oh, that's not true, and you go ask your friends, okay? Yes, now I have convincing evidence because there's only 19% of people. Well, how likely were we to get to 19%? So we calculate the standardized test statistic. When we calculate that standardized test statistic, we say, here's what I got, here's what it was supposed to be. What's the difference between those two things? Put that over the standard deviation of what it would have been if I had the null hypothesis. Find that it's below and what the probability of it being that low. So this was almost 2 standard deviations below the mean. Is that unlikely? Well, what we found was there's actually only 3% chance that could happen by chance. And so it's not likely that we just happened to pick a group of people that was a 19.5% chance. It's really unlikely that happened. So we have to say, yeah, it's probably not true that it's 25%. It's probably less because most samples were probably like this, right? So that would mean we have convincing evidence against the null hypothesis, which was it was 0.25%, or sorry, 0.25 probability of someone having a job after school. So that's how that works, guys. So that's how doing a standardized test statistic, finding it works and finding that p-value and evaluating it against the null to make a claim. All right, so the next piece is, excuse me, again, what if it's not the case that we just want less than? So what if we don't want it to say, oh, I think that the proportion of students who have jobs is less than? What if I just want to say, yeah, I think it's different than that? Meaning it could be less or it could be more. How do we account for that? And so what we've been doing so far is we've been doing this one sample z-test for p. We've been doing a one tail, like one of the tails. And so what we're about to do here is we're about to start a process by which we logically think through what does it mean for something to differ from a claim, right? So if I say 25% of students have a job and I ask 3 people and they're like, no, I think it's more, no, I think it's less. So all of a sudden, I'm saying, is it more? Is it less? What is significant? What's a significant difference? And so we got to have a plan for this. So here are the 4 steps for doing any of these significance tests. Here we go. 4 steps. Let me grab a different color here. Okay, 4 steps. Step 1 is to state what's going on. So for example, I got to state the parameter. What is it that I'm trying to measure? What is it that I'm trying to investigate, right? I have to state what the statistic is. I have to state the hypotheses. And I have to know what the alpha level is. Why do I have to know the alpha level? Because at the end, I'm going to come up with this conclusion. I'm going to say, hey, here's my p, 0.36 or 0.036. What does that mean? Okay. I have to make a plan. What test am I doing? How am I going to carry it out? So what's the name of my plan? And what are my conditions? Right? Because I can't actually carry out the test unless I have a plan. So what I'm going to do is I'm going to draw some pictures. I'm going to do some calculations. I'm going to show some formulas to show what is it exactly that I'm doing. And to do, I need to talk generally. Then I need to get specific. I also need to have pictures, work, and I need to have my answer. And for those things to happen, here we go. One of the parts is going to look like finding the test statistic. Right? That's going to be my stat minus my null over my standard deviation. And so specifically, finding z, which is equal to p hat, which is my stat, minus my null, over square root of p times 1 minus p over n. And Then I'm going to make my conclusion. We're going to say something like this. We do or do not have enough evidence or convincing evidence against the null. Okay, so we do or do not have convincing evidence against the null. And so what we're doing specifically in this lesson that I told you is if it differs from the null. Not is it less, not is it more, is it different than the null? And so what we're going to do is we're going to do a two-sided test. And really all that means is we are trying to figure out one of the tails and multiply it by 2. So we're going to multiply the p value by 2. So we're going to multiply the p-value by 2. So the steps are going to be the same, but we're just saying instead of less than, we're going to say less than or greater than. So here we go. Here's a problem. According to the National Institute for Occupational Safety and Health, job stress poses a major threat to the health of workers. A news report claims that 75% of restaurant employees feel that work stress has a negative impact on their personal lives. So think about that. That news report, that's probably going to be our null, right? Because that's the claim. Managers at a large restaurant chain wonder whether this claim is valid for their employees. That's what you do, right? I hear this claim, I'm wondering if it's true. A random sample of 100 employees find that 68 answered yes when asked. Does work stress have a negative impact on your personal life? So the question is, this manager's findings, this 68%, quick mental math there, is there convincing evidence at the alpha equals 10 significance level that the proportion of all employees in this chain would say yes, differs from 0.75. So, claim is 0.75. This manager got 0.68 at an alpha level of 0.10. Is there convincing evidence against the null? Is there convincing evidence to say, nah, that news report is phony? That's not true. So, let's state our parameters. In this case, the proportion, P, is going to be equal to the proportion of employees who say yes. It has a negative impact on their personal life. Our hypotheses are this. From the news report, H sub 0, P equals 0.75. You see how that's significant for me to say the people that said yes. Our alternative hypothesis in this case is not less than, and it's not equal to, or sorry, it's not less than, it's not greater than, because in this case we're just saying, is there evidence that it differs? This means that we're doing a two-sided, because it's not saying less than, it's not saying greater than, it's saying it could be either or, but it's just different nonetheless. So our alternative hypothesis in this case is that P does not equal 0.75, okay? Sometimes that's the hardest part, right? So you're just trying to figure out what the null is and what am I actually comparing to. So the rest of it is kind of just this math where I'm figuring out what was the claim, what exactly did the person find, and I'm plugging it into these formulas. Well, setting up the null hypothesis, because that conclusion is what's most important, right? Do I accept or reject? Well, if you don't have your null hypothesis correct, and you say you reject the null, then everything kind of gets messed up. So sometimes this is the hardest part. What is our exact statistic here? That's going to be our p hat. And our p hat is based on what the manager actually found. So that's our 68 out of 100, which is 0.68. So as we look at that, we're evaluating it at a significance level, and this is interesting that they put it at a 0.10. It's possible. And so what we're saying is if the probability is above 0.10, we're going to say, no, chance, probably could have happened by chance. If it's below 0.10, we're saying couldn't happen by chance, we need to investigate this claim. What's the name of our procedure? Even though we're doing a two-sided one, it's a one sample because we only have one sample. Z-test for P, right? It's a one sample Z-test for P because how many samples did the manager take? Just one. We're going to check the conditions. Is it random? Yes, it says random. So he took a random sample of 100 employees. Yes. What's our evidence? Quotes. Random. Let's see. Does it meet the 10% condition? So it's a large chain. It made sure to say that. So we're going to say that 10% is less than 1/10 of all employees. Is our large counts met? Well, let's think about this for a second. 100 times our 0.75 here is equal to 75. Almost got me there. And then 100 times 0.25 is equal to 25. Both of those are greater than 10, so we are good. Okay, now we're doing our general formula. Our general formula would look like this. That's the one for our test statistic. That's going to be equal to p hat minus p over the square root. Made my square root big enough this time. P times 1 minus p over our n. Okay. So now, what does it actually look like? Specific formula. Oh, I did that one for our. That one should go over here. Our test statistic is stat minus null over standard deviation. So anyway, we have this formula here now. So let's plug in our values. What do we actually have? Well, in this case, our z is going to be equal to 0.68 minus 0.75, what the manager found, minus the null, over, under our square root goes 0.75 times 0.25 over 100. And that's going to be equal to negative 1.63. Think about that for a second. Does the answer make sense? Well, our test, the manager's experiment was 0.68. That is below 0.75. So it makes sense that the z-score is negative. When we account for the standard deviation, what we're saying is this is over 1.5 standard deviations below. In my head, I should be thinking, the farther I get from that claim, right, that mu in the middle, right, the more standard deviations that go away, the less likely that it is. The one wild card in my own head right now is that alpha level of 0.10. If I put the alpha level at 0.10, is 1.63 above or below enough to say that we reject the null? I don't know yet. So let's draw a picture. Curve. What we're looking at is, here's negative 1.63. But what we're talking about is does it differ? And so we're actually looking at this above as well. So we're actually looking at the probability of this or this happening because we're thinking about it being different from the null. So this is what makes it two-sided. So what is our test statistic? Z is equal to negative 1.63. Our p-value is going to be from, you can either use your calculator or you can go to your table. Our p-value is going to end up being 0.0516. I wrote a 3. And I'm going to multiply that times 2 because we have two sides here. So that's 0.1032. So what does that mean? We just found out that it differing from the 0.75, there's a probability of 0.1032. When we compare that to our alpha, we see that it's above our alpha. So what would our conclusion be here? Well, our conclusion is, if we assume the proportion of employees that say yes is 0.75. That's what we did. We took the claim at its word and we evaluated that to find our test statistic. There is a 1 there is a 0.1032 chance probability of getting a sample proportion, which is what the manager got, a sample proportion catch this, guys, of 0.68 or further, right? Because this tail says, yeah, it's that 1.63, or it could be further. By chance. So it's a 0.1032 probability of getting 0.68 or further. So that means either 0.68 or lower, meaning 0.68 said yes, or 0.67 or 0.66 or 0.65, right? Or the other way. So this would mean that because it's above the alpha level, we fail to reject the null. We fail to reject the null because it's not below our alpha level. So this could happen by chance. So when we look at this next part, it says a 90% confidence interval for the restaurant worker data was also created and found to be 0.603272, 0.756728. Explain how the confidence interval is consistent with but gives more information than the test. So think about this for a second. If they created a 90% confidence interval, they said in many 90% confidence interval, 90% of the time, the true proportion of people that said yes is captured in the interval from 0.6032 to 0.7567. Well, we know, so this null hypothesis puts our proportion of people that actually do say yes at 0.75. That's in the interval. So if it's in the interval, that means that 90% confident that it's in that interval. Well, if it's, that 0.75 is in there. So the interval gives other plausible values though. So aside from just saying, hey, great job, your 0.75 is in the interval, it could be possible. We don't reject the null. We also say, well, but 90% confident that it's within here. And so we can look at other values and say, are they close? Would they fit in that 90%? So what do we say? The null value is 0.75, and it is in the interval. So it's plausible. But the interval gives other plausible values. That's the upside of the interval, right? You get that interval, you can tell kind of a range, whereas we just tested one specific value that some manager found. And if somebody came along and said, well, what about 0.65? I'd have to go back and do the the two-sided test again. Whereas if I had this interval, I could say, oh yeah, 0.65, that's in the 90% confidence interval. Good. Okay, so they have their upsides and their downsides, but they're all kind of related. All right, that's how it works, guys. So know that four-step formula. Make sure you check your condition. So name your procedures. So outline your stuff, right? So we outline our parameters, statistic, hypothesis, significance level. Then we're going to plan that procedure, name it, tell them what you're going to do. Absolutely say, when I test my conditions, does it meet that random? Does it meet that 10%? Does it meet that large count? Outline your general formula, use a picture to kind of help you and say, this is what I'm doing, this is what it looks like, and then apply those numbers into that formula. Don't just leave a bare formula or a naked answer, because if they don't have any context and you get it wrong, they're not going to be able to help you out. So try to outline as much as possible. That way, if you do happen to mix up one of your proportions or something like that, they can kind of say, yeah, you were on the right track. We knew exactly what you were trying to do, but maybe there's a little execution error there. So, or, get them all right, and then we're good to go. So just kind of outline it all so you can make a clear picture of what you're trying to do, and then write up those really solid conclusions using rejecting the null or not. All right, guys, thanks for watching, and we'll see you next time.